Hey guys, looks like I'm not going to be with you on Tuesday either, so I went put this together for us so we can kind of keep on track with some of our math. Um, as we get going on, I just want to, prep you up. I'm not going to be able to be walking around class and listening to your conversations you're having as you're working through problems today. So I'm just going to I need you to make sure that you're doing a really good job with those conversations with your table partners. And then, again, if something seems a little confusing, that's cool. Go after it. Get it wrong if you need to, and I'll tighten it up at the end. So have those pencils ready to go. And I think you'll do really well today. We're going to take our function notation, and we're going to kind of take it to the next step. So we're going to look at some functions, some rules that describe our functions, and you're going to be really good with these. And we're going to get that into our function notation, and we're really going to be looking at tables, equations, and graphs today. This is your warm-up. I think you probably already did it by the time you watched this video. So some things I jotted down in case you needed to jot anything down for your notice and wonder is I noticed that a lot of our tables we've been looking at with functions, they have the words input, output. And these ones don't have those words. So I'm kind of wondering, in our tables, do I still have an input and output? The next thing I noticed is it looks like I have two different functions. We were talking with function notation, having different ways to represent different functions. It looks like I have function f and function g. And I also noticed if I took whatever my x value was and I substituted it into my function, I got the output in the table. And it worked for both function f and function g. So I was kind of wondering, where these rules came from. What's up with a variable x on left side and right side? Because usually for solving an equation, it's x equals. So those are some of the things you might be wondering as you're looking at this before you have today's lesson. So just to reiterate some aspects of a function, with a function we have a value that goes in, a function of something. We used those function sentences earlier in the unit. And then this one is for the g function, a cube of the input. So let's say 2 goes in. It gets cubed. Our output then would be 8. So the input-output relationship using function notation in this case then would be something like this. G of x equals x cubed. So the function of the input, x, equals whatever that is cubed to give our output. So you can see that in your function notation table from the notice and wonder. So this is how it would look in function notation right here. The function of x is cubing that input. So feel free, if you need this paused, let the sub know. Get it paused and write down anything we have here. So this is where we're taking that little function notation stuff we had again and getting it into a rule. And this would work for any of the values. So if we have that table, let's rewrite that table right here actually. The x and then g of x equals x cubed. So if 0 goes in, 0 cubed is 0. If 1 goes in, 1 cubed is 1. If 3 goes in, 3 cubed is 27. And last, if x goes in, we're getting x cubed. So instead of input-output, we're just really using our function notation. You might also notice that this whole side here, the output, we have also used the letter y for that. But now that we're claiming we have this function, we're going to use function notation. So for 4-2 with your table partner, you're going to do a few things here. First, I think this part will go pretty quick. Uh-oh, I messed up. One sec. All right, I fixed it. So you're just going to match function with the letter that explains what's happening with your function, okay? So that's this first one right here. Then you're going to match when the input is 6, the output is -3. You're going to do that here. And lastly, you're going to evaluate all the functions for an input of 0 and an input of 10 to see which one is greatest. So please pause the video. I think we could be in the range for these 3 things, 5 to 10 minutes. So just make sure you keep an eye on the class, and then you can start the video up to get the summary. All right, so now that you've had some time to look things over, let's match things up for the first bullet. the top one there is going to go with C. Multiply by 3 and then subtract 7. The G function is going to go with B. Subtract 7 from the input and then multiply by 3. The H function goes with D. We're going to divide by 3 and then subtract 7. And then the K function goes with letter A. We're going to subtract 7 first and then divide by 3. All right? So there's our results. Now, which function has, when the input is 6, gives an output of -3? I found that to be function G. And I know this because, watch this function notation. The function of 6 is 3 times 6 minus 7. So the function of 6, G of 6, equals -3. 6 minus 7 is -1. Times 3 is -3. And then for this last bullet, I'm going to summarize, just kind of summarize it. I'll give you the two answers and then tell you how I got there. For the first answer, I got the greatest when the input of 0, I got K of 0. The function of 0 there, I got an answer of -7/3 for my K function. So I did that, I went up here, and that means the function of 0, that's where I got -7/3 right here by plugging in 0 for X. And then the greatest for the 10, I believe I got K. Nope, I lied, F. F of 10, and I got an answer of 23. The function of 10 is 23, and the K function of 0 is -7/3. So to test these all out, just to summarize what I did is, I went and slapped a 0 in every one of these to see what was the greatest, and -7/3 was the greatest. And then for the F function of 10 here, to get the greatest, I slapped a 10 in for X everywhere here, and 23 was the greatest I got there. Had a lot of negatives for the zeros, I think probably because, right, the subtraction, -7 happened. Yeah, those are the answers for that. So again, let me just show you another one. Let's show the F of 10 out, just so you can see how I worked that function a little bit. So the function of 10 is 3 times 10 minus 7. So the function of 10 is 30 minus 7, or 23. And that was my largest function of 10, F. So right here and right here are the two answers for that last bullet. So now I'm going to try to get you going here for problem 4.3, rules for area and perimeters, kind of get you started for question number 1. And then let you roll on it. We'll do a pause when I say pause, and then get you going on question number 2 and do the same thing. So really what's happening here is we know that a square has a side length of 9. And if we have a square with a side length of 9, we know that the area is 81, right? 9 squared. So this relationship always gives the area of a square as a function. So we're going to complete the table first. That's right here. You're going to complete the table. So if you have a side length 1, side length 2, what are the areas of those squares? Then you're going to write a rule for that function. And I'm going to challenge you to use function notation, right? So this is like a new thing. So the only advice I want to give you there, I'll get you started with it. You're going to do the function of the side, right? If you want to go back to our little function sentences that we were using a couple lessons ago, you would say that the area is a function of the side length. So right here shows a function of the side length to get total area. So I'll start you up. You're missing this side here to get the function notation. Then you're going to look at the function of side length of 2 and what that means in context. And lastly, you're going to sketch the graph. So this is probably going to take, I'm going to guess, about 8 minutes. So please, the sub or whoever's there, please just make sure you're keeping an eye on groups. Give it somewhere around 8 minutes, I would guess. And then when everybody's kind of finished up, I'll summarize the problem. All right. So I hope you had some good productive time with your partner. Let's work on filling out this table. So 1 squared is 1. For a side length of 2, 2 squared is 4. 4 squared is 16. 6 squared is 36. And s squared is s squared. So those are some of my potential squares. The area of my square is a function of their side length. So to get my rule, this is the big one. This is the big new one. The function of a side length equals s squared. This is going to be my rule. This is the big one for today. So that's function notation. What this says is if I take the side length and I square it, that'll give me the area of the square. So for B, what does the function of 2 mean? For B, what that means is that the function of 2 is the area in square centimeters when the side length is 2. Its value is 4. So again, to summarize, when we have a side length of 2, our square's area would be 4 square centimeters. That's what the function of 2 means in this context. And then I'm thinking this is one of the easier things for you. We have this little table or a little graph. So 0, 0, I got 1, 1, 2, 4, 3, 9, 4, 16, 5, 25, 6, 36, 7, 49. That one's not even on the graph, but right, we're squaring our input, our side lengths to get our outputs in area. And that would continue on forever. Excellent. We got one more piece here. It's going to deal with a roll of paper and perimeter. So this one I think is a little harder just to wrap our heads around the situation to start. So what it's saying is there's like that roll. Your picture in your notes is kind of better, and you can unroll it and cut it whatever you want. Just this side of the roll is always going to be 3 feet. Okay? So when it says A, if we cut a length of 2 feet, it's always 3 feet here. And that means I'm going to cut 2.5 feet here. And that other side's always going to be 3 feet. Okay? So this would be like after we cut it off the roll, these would be the dimensions. So if we cut a length of 2.5 feet, what is the perimeter? Well, I have 2 sides that are 3 feet for 6 feet, 2 sides that are 2.5 feet for 5 more, and I've got an 11-foot perimeter cutting off that roll. And like I said, I think the picture in your notes is better, a great visual. So what you're going to do is you're going to complete the table of perimeters from that 3-foot wide roll of paper. Again, just like what we did, you're going to draw, this is the big one, the big new thing kind of. You're going to get that rule and function notation, explain what the function of 11 is in this context, and then give us a little graph. So again, I think this one might be faster since we just did something similar. So 5 to 8 minutes is the goal. So please pause and give students some time to work. All right. So hopefully you and your partner had a really productive time here. So let's talk about this paper roll. So if a side length's 1, I'll draw a couple more of these out here. We know it's 3 feet on these sides. I got a 1 and 1. So that's a perimeter of 8. I want to use the same little image. Let's say it was 2 instead of 1. Right? We got 6 and 4 for 10. 6.3 and 6.3 is 12.6, plus the 6 is 18.6. If we have sides of 11 and 3s, we've got 28. So as we can see from rolling down our table, we've got this rule here. And the rule is if we take the length, we know we're starting with a perimeter of 6, right? These 2 3s every time on the sides of our roll. And then we're going to plus 2 times the length that we cut off. And that'll always give us the total perimeter. So what that's going to look like for our rule is going to be this. We're going to have the function for perimeter of the side length, right? The length is going to determine the output of perimeter. That is equal to the 6 plus 2L. So this is the function notation, and we write this because it is a function. So instead of doing like y equals 6 plus 2x, we use this notation to signify this is a function that's going to pump out different outputs over and over. Looking at C, just so there's more room, I'm going to write it down here. What does P of 11 mean? Well, P of 11 is the perimeter of paper in feet when the paper is cut a length of 11 feet. Value is 28 feet. That's what that means. So this references this image up here and this part of the table here. So the function of 11, side length of 11, pumps out a total perimeter of 28. That's what this function notation here says. P of 11 means that in context with our rule. So let's now get this on the graph. So side length of 1 pumped out at 8, a 2 pumped out at 10, 6.3 gave us 18.6, and those are all that fit. I'm going to go to a theoretical 0, 6. Can't cut 0, but the two side lengths are always going to be there because the rule is 3 feet wide is 3. If I connect my function here, it's going to look something like that forever. Let's make the arrow a little better. There we go. Sweet. Well, friends, I think we did it today. Make sure you tighten up those notes. If you get home and anything doesn't seem right, you can always go back to these. I'll have it on the Canvas announcements as well. And I just hope that you continue to do a great job and be really respectful of the sub and work real hard. And I look forward to seeing you when I get back. Oh, one sec. We got to summarize real quick. I want to look at this with you real quick. Just to make sure we can make rules, make sense of rules. When they're written in function notation, we can use that to create tables and graphs. We did that 3 times. And then the thing that we really worked on today, and we're going to continue to work on right here, write the equations that represent the rules of the function. So we already know those rules. We already know how to write equations. Just making sure that we're writing in function notation is kind of the big new thing today. All right, family, be good.